function in question is what?
Sine squared x.
So I'd like to know the Maclaurin series for sine squared x, right? So you can do this directly using the methods from 6.3, where you would find the derivative, the second derivative, the third derivative, fourth derivative, and then evaluate each of those at 0. And from that, you can determine the coefficients for the power series. That's one way to do it. But if we do that, it's going to get complicated real fast because the derivatives we're going to be using, well, if we have time, we might do it that way. Would that mind?
I think so, but it's still recording and it's
Okay.
nothing.
Oh, maybe it's
It might have been that one. Yeah. So as an alternative, it helps to know some trigonometry. The trigonometry might make the calculus easier. For example, in this case, it's well known that the sine squared is the same thing as 1 plus cosine 2x over 2, or in other words, and that's the hint,
Oh,
right?
is that what you did right here?
It's given here.
Yeah. So with this hint, it makes this a lot easier actually. And to appreciate how much easier it is, we should try and do this. You know what I mean? With the normal way, the 6.3 way, right? Using the formula for the coefficients. So let's go ahead and do it both ways. Which way shall we do it first? The hard way or the easy way?
Chronological, so 6.3 first.
Okay.
If we're gonna do it here.
Yeah. Well, I mean, the 6.4 way could have been done in 6.2. This is actually very similar to that question on the exam, right? So like, well, yeah, so like in 6.2, this question could have been asked, okay? So if we're gonna do it chronologically, I'll do it the 6.2 way, right? So we're just looking at some applications. So I know that the cosine of x, if I already know the Maclaurin series for that gives me a huge head start. Because I know that that can be expressed as, you know, and this is something that might be worth memorizing, right? But it's all the even powers of x. So it's going to have an x to the 2n, where n is going from 0 to infinity. And the coefficients, however, is going to be 1 over 2n, the same exponents, but with the factorial. Furthermore, this alternating, where this is an n. And this is for all x. So the radius of convergence is infinity. Okay? Something worth knowing. So if you already know this, then I can use this to come up with that. For example, I can see that the cosine of 2x could be computed by doing just simple substitution. See that? And so now it can be seen since this is a product raised to a power, I can think of this as 2 to the 2n power times x to the 2n power. So I still have just strictly even powers of x, but the formula itself for the coefficients has changed a little bit, right? And in fact, I can go a step further and say now that the sine squared x is equal to 1/2 of 1/2 of this.
Professor?
Yeah.
So when you do this, she still need to check the rate. I mean,
Radius of convergence, yeah.
Right.
Good point. So if x can be anything, then what would be the radius of convergence after I do the substitution, right?
Say it again?
If x can be anything, what could 2x be?
Twice as big as anything.
Basically anything,
Yeah.
you know? So yeah, that is something that we should think about, right? Or if, and then right here, from here to here, I just did algebra. Yeah, so this is still gonna be for all, I guess technically I should say for all 2x, right? But whatever 2x is, there's an x that corresponds to it, that I could double to get it. So it literally is for all x. So that's your power series right here, okay? This can be simplified a little bit because by combining like terms. Combining like terms. Inside of this summation, there's a whole bunch of terms that are added together, all with different powers of x. But notice that when n equals 0, this is going to be x to the 0th power. The first term in this series is a constant term, which I can combine with that constant.
Okay.
See what I mean? This is my answer, but I just want to simplify it a little. I'm just combining like terms. So I'm going to write it like this. I'm going to continue on right here and say this equals 1/2 plus 1/2 of, again, I'm going to plug in 0. I'm just going to show the first term right here and put everything else starting at 1 going out to infinity, right? This I can just copy down. The first term here is when n equals 0. When n equals 0, that's just going to be positive, that's going to be 1, that's going to be 1, and that's going to be 1. Right? So I would probably submit my final answer like this.
And you need to put 1/2 as well because it's multiplication.
Yeah, thank you. I missed that. So I distribute the 1/2 here, I distribute the 1/2 here. And in fact, you know what I can do?
2n minus 1?
Yeah. If I bring in the 1/2, it's 2 to the 2n divided by 2. I just make it like that. That's a little nicer. So now it's clear to me that these are my coefficients. Right? That is my formula for the coefficients to generate this power series. Actually, in this case, I should probably call it a sub 2n. It's the coefficient for the term of that degree.
But still, that form is fine, though, or?
Yeah, I think so. I mean, I guess, I don't know. I guess it kind of depends on the teacher you have.
Okay.
You know what I mean? I think really like to determine the power series, you want to determine all the terms. You know what I mean? If you were to expand this, if you were to literally write this out, it would look like this, right? it would be, let's take a look. If you were to expand this out, it would look like 1/2 plus 1/2 of when n equals 0, which we saw as 1. Plus the next term, which is when n equals 1. When n equals 1, I have a negative over 2 factorial. That's negative 1/2. Oh, wait, 2? Oh, that's going to be 4 factorial. No, wait. N equals what? What does n equal to? Here is where n equals
So
0. Here is when n equals 1, n equals 2. I'll go up to 3, and then hopefully by that time it'll be clear what the pattern is. When n equals 1, yeah, that's going to be a 2 factorial. So negative 1/2 times, so let's say, minus 1/2. Actually, it's 1/2 of 1/2, right? So 1/2, 1/2, but if n equals 1, that's going to be 2 squared. That's 4 times x squared plus 1/2 of, that's going to be so when n equals 2, 4 factorial, that's a 24, I think, times, n equals 2, that's 2 to the 4th, so I think that's 16, right? Minus, 6 factorial, 720 maybe? Times, when n equals 3, 2 to the 6th power, 2, 4, 8, 16, 32, 64. So yeah, so I think in this form it's a little more obvious, right? That, you know, these two guys ought to be combined, right? The rest of it, you know, in an expanded form, you really are kind of inclined to cancel all these 2's. There's tons of 2's to cancel, right? But that's not really, but that kind of obscures the actual pattern, right? So yeah, so the pattern holds for all these terms except for this one. So we just gotta kind of think of it as a computation unto itself. So yeah, yeah, now that I talk it out, I really think you ought to combine these two terms. You know? So notice that we found the power series without taking any derivatives at all.
I didn't find it.
Notice that one could conceivably find the power series without taking any derivatives at all. And you know, it is a little bit of a challenge to put it in sigma notation. You know, you could also do it in this form just as well. Yeah, I think once you get used to sigma notation, I think it's a little faster to be able to do it that way. But yeah, but you strictly speaking, using the formula that we derived in 6.3, I think what I'll do is I'll use the formula to determine maybe like the first 2 or 3 terms, just to see if it matches up. And fingers crossed, it should give you the same thing. But I think this way it's easier and faster. So if it can be done with substitution, so using that formula is really something, a last resort. You know what I mean?
It's supposed to be T right here, right? DT.
Oh, yeah.
Wait a second. F of 0 is 0, right? Sines of 0 is 0. Sine squared of, the square of 0 is 0, right?
Yeah.
I'm a little worried because the first term is 1. And the first term should correspond to the value. Yeah. But, let me think here. Oh, that is what it is. Let me make sure I'm remembering yeah, and this is the hint, right? I'm remembering this right? Is that what it said in the book?
Right.
Is that the given one? 209.
That's not a minus.
Oh, it's minus.
Oh! Dang it, my trigonometry is a little bit off. I was, now see, the reason I was worried is because I know that whenever you use this formula, the value of the function at 0 always matches that first coefficient, which we saw to be 1.
Oh, so which means you just solved the 208.
Yeah. Oh. Yeah, this is not 209, this
Oh,
is
yeah, it is.
208, the actual homework problem.
Yes. Yep.
Good point. So yeah, so for 209, that should be a minus, and that should be a minus.
Wait a minute. I didn't get that for 208 either. Okay.
I'm changing this right here to a minus. So change this to a minus, this to a minus, this to a minus, which means that this is a minus, this is a plus, this is a minus, this is a plus, and it alternates from there on forward. It means that this is a minus, means that this is a minus, and that's a minus. 1/2 minus 1/2 would be 0. And if I bring that, I can bring this negative inside. I can, just like I distributed the 1/2, I can distribute the negative and just put. You just have one, I'm just multiplying by one more negative.
Yeah. Woo. This is rough to me.
You know, I just wanted to get this far at least in the derivatives to see that to use our formula, it starts getting pretty complicated pretty quickly. Notice I had to use the chain rule to come up with this. I have to use the product rule to come up with this. And I guess actually it's not that bad because oh, actually that's 2 times cosine squared x minus 2 sine squared x. So to continue on, I'd be using the chain rule twice, and then it's gonna kind of continue on from there. But it's not as predictable a formula as we have seen before, like with e to the x or sine or cosine alone. So to compute all of these is difficult. Right? Because in order to come up with that, I need to not just compute these derivatives. I got to go far enough to see a pattern in the derivatives.
I was thinking because like if you convert to if you plug in like 1 minus sine x instead of like 2 cosine square x, then it will be 1 minus 4
Yeah.
sine x, and then it will drop all the like constant number.
True. Yeah, so you can use some trig identities here. But if we're going to use trig identities, we might as well do it at the very first step. You know what I mean?
Yes.
And if we do it at the very first step, then we're doing it the better way.
Makes sense.
You know what I mean? Yeah. Yeah. But at least I did get this far at least. I can see that the second derivative valued at 0 is 2. Right? And according to the formula, a sub 2 would be the second derivative evaluated at 0 divided by 2 factorial. I know that this is 2, that's gonna be 2 over 2, that's just 1. Is that true? Oh yeah, look at that. See right here? 2 squared over 2 squared becomes just 1. If we had simplified this coefficient in front of the x squared, we would get 1.
But isn't n, when n is equal to 1 and that one is,
Well, this is not the same n as over there. Remember, so if we're using this method, right, we're assuming that if this is the case, then we would say that a sub n, if this is f of x, would be the nth derivative valued at 0 divided by n factorial. But that's where this is x to the n. When n equals 2, that's the coefficient for x squared. Here, n equals 1 because of, maybe I should have chosen a different letter here, right?
oh, right.
But yeah, when n equals 1, that's the coefficient according to that index that's the coefficient for x squared, right? This is the formula for the term that corresponds to the x to the n.
Oh, because we changed it.
Mm-hmm.
Is this whole thing supposed to be factorial?
No.
Just this one?
Right,
Factorial.
right, just this one.
Okay.
I just need a
Mm-hmm.
let's bring it back a little bit. So if I have a function, right,
Yep.
such as whatever sine squared x,
Mm-hmm.
I plug in like any random value, and like the calculator will give me the answer to that, right? If I plug that same number into the sequence right now, it'll be very, very close, right? Just like
As long as it kind of depends on how far you go.
Right,
You're not
right.
going to be able to literally go out to infinity.
Well, right.
So you got to decide how far you're going to go.
Yeah, and the
So-
closer I get, the
Yeah.
more of a
So the further away you are from 0,
Right.
the more terms it will be necessary
oh,
to attain the same level of accuracy,
okay.
right?